Okay, welcome to our project demonstration on plant leaf disease classification using the CRNNS. And this project was developed by me, I am Shahan Anwar, and my groupmate Ms. Mashraf as a part of our MSAI coursework. So let me show you the dataset organization here in the Google Drive. I am going to the Google Drive with the folders in it. That is plant unit splits. So I have this plant unit splits folder containing the three subcategories folder, subdirectories, the train, the test, and the validation. This is how we split our dataset. So we will go to the train folder and I will show you all the 15 diseases that a plant can have, such like as a paper bell bacterial spot, the paper bell healthy, early blight, healthy, late blight, and just like for the tomato and tomato virus and yellow leaf, bacterial spot, and leaf mold. So the training folder contains 15 different diseases categories, including the pepper, potato, and tomato disease. So each category has its own folder. Why do we split? The question is that why do we split this into the the multiple folders into the validation, test, and train. The training set with the 14,044 446 images stitches the model. The validation set with the 3000, as you can see, 3096 images monitoring the training process. So just like that, we have the test dataset that have the 3096 images evaluates final performance on the unseen data. So this is the folder that it contains all the data in it, and after that the splitting shows that we can properly evaluate how well our model generalizes to new disease condition. So let's come to the some images. So I will show you some images from the different disease categories. First, as you can see, this is the paper bell bacteria, and if we go onto the back on the test, and if we click onto the healthy folder, and click on this, yeah, you can see the test, the healthy in it, and after that, if we go into the late blight, as you can see the different images, this is all the late blight. So this dataset has been split it into the different folders. So I will go into this, and all images are resized by the 1 to 8 by 1 to 8 pixels. As you can see, I will show you the file information, and you can see all the images information here. So it has the 15 different disease categories. So let's come to our code. First, we have the code in which we mount a Google Drive to access our dataset and store into the cloud. Then we import all the necessary libraries, as you can see, the TensorFlow and all the important other libraries. What do we need it? Because TensorFlow and Keras for building our neural networks, NumPy for the numerical operations, Matplotlib library, and the Seaborn for the visualizations. And we also import the special layers like Convert2D, GRU, as you can see all of them in it. This is the and that that we will use to build our model by suppresses warnings to keep our output cleaned and focused. So that's why we are suppresses our warnings. So this cell is all about demonstration. Here we set up the configuration. What does this do? We define the base path pointing to our plant village splits folder. We create paths for the train, validation, and the test directories. As you can see, we have created that. We have 3 folders: test, train, and validation. So this cell does this. It splits them into the different parts. So we also set our hyperparameters image size of 1 to 8, as I told you before. And batch size of 32, we're going to set it into the batch size of 32 and epochs of 20 for the training, and learning weight of 0.0001. So why we are these important? The question arises: the control how our model learns and processes the data from the multiple classification. Next, we come to the our data set loading. So we load our data set. So how does this work? We use a TensorFlow image dataset from the directory function, which automatically reads images from folder, organizes by class name, what parameters we set, image size 1 to 8, and all the things. I am going to show you that. Okay, so what parameter would we set? We set the batch 32 categorical labels for multi-class classification and seed 42 for the reproducibility. So as you can see, this is the data set we have loaded. So let's come to the next, our data augmentation, because we are doing the data augmentation and processing. So because we have limited training data and only 15 classes to learn, how does it work? We create a comprehensive pipeline that randomly flips images horizontally, rotates them to the 20% zooms in or 20% zooms out. So and translates images by 10%. So when does it apply? Only to the training set. For validation and test sets, we only normalize pixels values by dividing by 255. We also add prefetching to optimize data loading speed. So this helps the model learn to recognize disease in different conditions across all the 15 categories. So this cell is all about building our model building code. So we are building our CRNN model. We start with an input layer accepting 1 to 8 by 1 to 8 by 3 images. So what comes next? As you can see, the CNN feature extract with our 4 convolution layers. The first uses 32 filters to detect these basic features. Each layer doubles the filter by 64 by 2128. As you can see, 64 and 128, and then the 256. So it is used to detect more complex disease pattern as we go deeper. Each convolution is followed by batch normalization to stabilize training and max pooling to the reduced size. So how does this help? It makes the model efficient and focuses on the important disease feature. As you can see, we have these layers, and we have these total params, and we have the trainable params, and we have the non-trainable params also as well in it. So after CNN layers, we ship by 8 by 8 by 256 features into the sequence of 8 times 7 with the 2048 features. So we have to convert the spectral features into the sequences that RNN can process. The GRU layer with 256 unit processes the sequence remember spectrum across the image. So finally, the classifier has a dense layer with the 256 units drop out only 50% to prevent overfitting. So we have to prevent the overfitting, we have to prevent the underfitting, and a final dense layer with the 15 units of the multiple classes. So we have the model summary. So we compile the model with the Adam optimizer and the categorical class entropy loss. The model summary shows we have this 230, 991, and 8.51 megabytes model. This is larger than the binary classification because we are classifying 15 different classes. So basically, we set up 3 callbacks. We are callback 3, they monitor the training, make adjustment automatically, always stopping batches, validation accuracy, and stops if it does not improve for 5 epochs. So model checkpointing saves the best model during the training, learning rate reduction decreases the learning rate by half in the validation loss stops. So improvement for the 3 epochs. So these are important, they prevent the overfitting and ensure we get the best performing model for the multi-class classification. So basically, we train the model for 20 epochs. As you know what happened. So the model learns from the training data and validates on validation data after each epoch. You can see the training progress accuracy start from the 38, 0.38, and in each epoch improves to the 195.85, as you can see in each after each epoch percent. So validation accuracy reaches 83.07%. The learning rate automatically reduces when needed. This shows the consistent improvement across 15 disease categories without significant overfitting. So here we are saving the model, and after training we save the model and we print after. As you can see, we have this model in our, as you can see, the plant disease model of CRISE. So we have saved this model here, so we can after training we can save it and we can use it later on, and the test accuracy is 82%. So requirement was 75%, so it is greater than 10. So here we have the configure matrix. We generate a configure matrix, how we make prediction on all the tests. As you can see, so images compare with the true label. What does the configure matrix visualization displays a 15 by 15 grid, as you can see, and incorrectly classified for each disease category. We can see the model correctly identifies most disease categories with a good accuracy. Some confusion may occur between the similar disease, which is expected in the multi-class classification. This helps us understand the model's performance in detail across all the 15 classes, as you can see on the x-axis and on the y-axis also as well. So at the end we have this model. We are running this test for testing that, as you can see. So it will connect to the Google Drive. So then I told you we have that save model, and it is testing. It has asked me access for the Google Drive, and after that it will load the model and predict the class, and it uses the save model that we have saved here. So it will use this, and we have some images in the test. As you can see the test image, and we are loading this image here. So it, as you can see, it's been mounted, and we can simply, as you can see, the test 3 image. So this category, as you can see, this is a test 3 image. So it has the bacterial spot, or it has the disease or not. It will classify it, and you can see the model works successfully. As you can see, we have these models, and after that we can simply, as you can see, this. So this is the tomato early blight, as you can see. So we have this, and we can also test one of these images. As you can see, this image is correct, so we can simply go to it. We will change the path, and we will save it, and we will test on it also. So it will show that we don't have to mount. It is saying that don't mount because it's already been mounted. So after that it is saying that we don't have this file, because I think so this file is in the JPG format, as you can see. So we have to rent it. So as you can see, it's having, and you can see it's been healthy declared. So this is the predicted class, and it is paperable healthy. So it's all because of this. Goodbye.